My name is Carson Allen, and this is Lab 1 on constant velocity for Physics 2211. The purpose of this lab was to demonstrate constant velocity as we observe the position of a rolling object over a short period of time with the tool tracker. The purpose was to demonstrate Newton's second law, which we can rearrange to find our velocity update formula. The purpose of this was to show if we have a net force of 0, the velocity will stay constant, or in other words, final velocity equals initial velocity. And that can also be shown from Newton's second law, which can be used to predict our positions and have some minor errors in our final result. For deriving the velocity update formula, it can be seen here. Mainly we convert change in momentum to mass times change in velocity, and then we do some more algebraic manipulation to find velocity equals initial velocity plus net force divided by mass times the change in time. We got this originally from the net force is equal to change in momentum divided by change in time. Now if we let the net force equal to 0, we can see we have a constant velocity, or final equals velocity. For systems versus surroundings, our system was a bottle, which is pictured on the right. It was full, so it had a decent mass at the time. For our surroundings in the y direction, we do have the force of gravity and normal force. However, these cancel out, and we also have a force of 0 in the y direction, so these are relevant. We do not have perfectly expected net force of 0 in the x direction due to friction, which is inevitable. It is rolling friction, which does minimize the effects of this. However, it will still create some minor differences in our observed versus expected results. Our initial conditions, we found the velocity by deriving it from velocity equals the change in displacement divided by change in time. This was about 360 pixels and 1.7 seconds. This led us to about 217.78 pixels per second. Our initial position was x equals 0, or at the origin. We had an initial time of 0 seconds. Pixels were measured with the tracker. The actual measured distance of observation from start to end was 1.5 meters. Since this is a proportional difference, whereas we could just divide by a constant, the graph will still look the same visually. It'll just be a different scale for displacement on the y-axis because it's pixels rather than meters. For our experiment, you can see a bunch of the expected values on the right. A graph will be shown later. But over the course of 1.7 seconds, we tracked the position every 1/30th of a second manually. The initial values in the tracker did start at negative 98.68 pixels. However, this was later readjusted by adding 98.68 to each position when comparing it to our computational. In addition, the ball rolls away from the origin in the negative direction. This increased the magnitude of our displacement appropriately. However, so we just have to multiply by -1 to get appropriate comparisons for our graphs later on. The velocities at each interval is shown on the very right-handmost column. Though it's not entirely accurate because manual marking of each position at tiny frames can lead to big differences, the general trend shows the velocity is decreasing in magnitude, and this is again from the expected rolling friction. For the computational prediction, we had the constant net force of 0, which led to a constant velocity. This only leads us to having to update the position of the ball, which is going to be the previous position plus the velocity times delta t. We use delta t as 1/30th of a second again. And in addition, we started our initial position at x equals 0 and t equals 0. We also had the velocity going in the positive direction, which recreated the graph as seen below. Now for our results in potential error. So after adjusting the tracker points to the same as our computational, you can see the graph there. You can see the observed has a slight curve, which shows that it is slightly decreasing in speed. This leads us to underpredict some of our values, our computational model, although very slightly. We expect this error to come from our friction and experiment, which we knew was inevitable. In addition, there could have been manual errors of tracking the position, each frame, and then also due to the shape of the bottle with the center of mass, it could roll at a slight angle rather than straightforward. However, our overall model is still pretty accurate. There's just some minor errors as listed previously. Now, what if we had changed our x and y axes? So our overall magnitude of speed would be the same, except now, again, everything would be multiplied by -1, which can be seen on the graph on the left. The magnitude would still be the same, and we would still underpredict the magnitude of the displacement slightly. Now, is it certain to say how many pushes or pulls in the x directions there are? So we know for sure there's friction, but there could also be some inconsistencies between each wood board or maybe some airflow from like air conditioning. And some other pushes or pulls I am failing to think of at the moment. Newton's second law states that the net force is equal to the change in momentum divided by the change in time. We can derive our velocity update formula from this. With this net force of 0, we find that our velocity is constant. We can use this to predict the position of any object very easily, knowing the net force is zero. This comes from our position update formula, RF equals RI plus average velocity times delta t. In the real world, there's almost always some force in the surroundings affecting our system slightly, not producing completely predictable results. However, we can still produce very accurate results like in this case. In the case of our experiment, rolling friction was this unfortunate thing that caused us to underpredict our results. Thank you so much.